So, could you please tell us about yourself?
Okay, well, my name is Paul Ronney, and behind me are my assistants, Hanya and Ileana. And I'm the chair of the Aerospace Mechanical Engineering Department at the University of Southern California. I've been at USC since 1993. Before then, I was on the faculty at Princeton University for 7 years. And before that, I was a postdoc at NASA, then called NASA Lewis, now called NASA Glenn Research Center, and the Naval Research Lab in Washington. And before that, I was a PhD student at MIT and working in the Aeronautics and Astronautics department. And I did my PhD thesis on the effects of gravity on fires.
So, why did you want to become an aerospace engineer?
Well, as an undergraduate, I was sort of a little bit more interested in the mechanical engineering side because, like a lot of kids of my age at the time, I was really into cars. And so I was kind of interested in that. But the more I got into it, more I got into my undergraduate education, I sort of saw aerospace, as a bigger challenge. And really, even at that time, even though it was post-Apollo, of course, I still saw it as being the challenge, as being the future. So I sort of deviated more towards the aerospace side of things. So my undergraduate degree is in mechanical engineering, but my graduate degrees, my master's from Caltech, my doctorate from MIT, are in aerospace.
So, you were an alternate payload specialist for a space mission. And how did you become a backup crew member, and what was the process?
Sure. Well, I had an experiment on that flight, sort of an outgrowth of what I'd done for my PhD work. I continued as a postdoc at NASA Lewis Research Center in Cleveland, and then even as a faculty member at Princeton. And the work progressed to the point where it was appropriate to propose it as a space experiment because we could get some very interesting results in the drop tower at NASA Lewis, but we can only get 2.2 seconds of free fall. And then we actually used the drop tower in Hokkaido, the island of Hokkaido in Japan, where they could get 10 seconds of free fall. But even then, it still wasn't clear what would happen because we really needed more than 10 seconds of low gravity. We did experiments also on the KC-135 aircraft flying low gravity trajectories where we could get up to 20 seconds. But the problem with that was the quality of the low gravity wasn't that good. That is, you could see the flames that we had ignited just sort of kind of floating all over the chamber in response to the little bit of gravity that there was. Even the best pilot can't keep it, wasn't really good enough quality of low gravity for us. So then I proposed it as a space experiment, and that proposal was accepted. And then it was manifested on a space shuttle mission with several other combustion experiments. So it was decided there would be a combustion specialist on the mission. And so, needless to say, my hand went up. So it turned out I was chosen as the backup. So I went through all the training. There was also a materials specialist on the flight. There was supposed to be a backup to that person also. Long story, but that backup dropped out. So I wound up being actually the backup to both the combustion specialist and the materials specialist. So I went through all the training, spent a year and a half commuting between Houston and Florida and Huntsville, Alabama, and other NASA centers and other faculty members, research laboratories to learn more about the experiments that they were doing. It was quite an experience. It would have been better if I gotten the chance to fly, but of course that didn't happen. Actually, the sort of reflight of many of those experiments was on STS-107. Which was, of course, the last Columbia mission. Under a slightly different set of circumstances, me having been the backup on the previous mission, I would have been on that mission. And in fact, at the time, I was disappointed that I didn't have a chance to fly in that mission. But of course, as it turned out, it was a good day to stay home.
So into your study about combustion, how can something like microscale combustion help in propulsion?
Well, the way I like to think of it is, if you ever saw the movie Finding Nemo, you say, where's he going with this? That, that one scene where the fish are kind of rearranging themselves in all different patterns. Well, that's what we'd like to do with satellites, with clusters of large formations of satellites. But they all need propulsion to be able to orient and reorient themselves and maintain a certain pattern. This could be for Earth observations, for radio astronomy, communications, lots of different applications to that. And the problem is small scale propulsion is just not very efficient. Typically what people use, either they have satellites with no propulsion system at all, or they use things like cold gas thrusters or even water vapor, just a flash evaporating into space, provides some thrust, of course, but it's really very low specific impulse, just not very efficient. So we're looking at ways of getting something closer to large scale propulsion efficiency in terms of the specific impulse than we can get out of current systems. So we're looking at thrust levels, particularly in like about the 10 millinewton to maybe up to 1 Newton thrust range, which is kind of the sweet spot for these small satellites. And there really isn't, a good propulsion system in that level. Yes, you can use chemical propulsion, but like I say, it's terribly inefficient. And what we found, one of the things that we found is that the same sort of de Laval nozzles that we use at large scales, the converging, diverging, is absolutely the wrong shape at these small scales, something that people haven't appreciated before. And we've done some optimization to find out, well, what is the best shape? So that's one thing, is finding the optimal shape. Because when you have nearly reversible adiabatic flow, that leads you to one type of shape. When you have smaller scales where the flow is not reversible, there are significant viscous losses, as well as significant heat losses. It's not adiabatic. Then that leads you in an entirely different direction. And by going in the right direction, you can improve your performance substantially than if you just took a big nozzle and made it small. So that's sort of what we're working towards in that area. The other part of it is we would like to get away from hydrazine as a propellant, because hydrazine is extremely toxic, very dangerous to handle. So we're looking at particularly nitromethane as a propellant. Nitromethane actually, as it turns out, has slightly better theoretical specific impulse than hydrazine. The problem is it's hard to burn. But because of my background, that's one of the things I've studied over my career, is how to extend the limits of flammability and ignitability. And so we're trying to do that, using, so the two aspects are the right nozzle shape, as well as, a new propellant that's, much less hazardous than nitromethane, and yet has similar, or actually even a slightly higher theoretical performance than hydrazine.
So what aspects of turbulent combustion are you studying?
Well, turbulence in combustion is one of those examples of you can have too much of a good thing. I say that in the sense that turbulence will increase the burning rates of flames, but if you stir it too intensely, you can actually decrease the burning rate or even extinguish the flame entirely for reasons that are still not well understood. And so that's one of the things we're trying to understand is, why does the burning rate start to level off and even decrease? And then why does it actually go out? So without getting into all the technical details, we're looking at what causes these flames that, at least according to the theory, they should just keep, as you keep stirring it more and more intensely, the burning rate should just keep going up and up. But experiments have shown for a long time that doesn't happen. And we're trying to uncover the reasons for that. And if we know the reasons, maybe we can do something better so that increasing the stirring intensity more and more can then continuous at the faster burning rate. And if we can burn faster, you say, well, okay, so what if I can burn a little faster? If we can burn faster, that allows us to use leaner mixtures that have lower temperatures, produce less nitrogen oxide emissions, and less soot formation, instead of the near stoichiometric mixtures that we currently use. So maybe limiting even the need for the three-way catalyst that we have in our current cars that need to oxidize CO and hydrocarbons and need to reduce oxides of nitrogen. So they have to work right at stoichiometric. We're trying to come up with ways of limiting that need, which would save a tremendous amount. I know it turns out in my neighborhood, there's a big problem nowadays with people stealing catalytic converters right out of cars just parked on the street. Because the catalysts in those catalytic converters is quite expensive.
Right. So what are the challenges associated with propulsion of robotic insects, and what are the applications of the technology successfully developed?
Yeah. Well, the applications of robotic insects, I think primarily are in the area of surveillance and reconnaissance. The example that I like to use is, suppose you're in I used to say Afghanistan, but of course we're not in Afghanistan anymore. Let's suppose you're in Iraq. Let's say you're a soldier in Iraq, and you think there might be, you know, something inside that building, but you don't want to, go inside the building. You want to see what's in there first. So if you can send out a little robotic insect to kind of look around and see what's there, see if it's safe to go in, or if there's something, that you want to counteract before you go into the building, that you can do that. The problem is, the same thing we do everywhere in the world every day at large scales, which is convert fuel into propulsive effort, is extremely difficult to do at small scales. People have tried to build very, very small internal combustion engines or gas turbine engines, but they have not succeeded. Because because it's this whole concept, like I said before, about trying to take something big and just make it small. This doesn't work for the same reason we don't have people the size of insects or insects the size of people, thank goodness, that we can't just scale down an internal combustion piston type engine or a gas turbine type engine to very small scales. So we're trying to use a very different approach, one that doesn't involve things with moving parts, with seals that can require a lot of heat transfer or minimization of heat transfer. So we're using alternative techniques, particularly based on the heating and cooling of chip memory alloy wires, which can be very thin, so they can have a very fast response time. And you can do that without any sort of active seal like you have in a piston cylinder engine.
Mhm.
So we think that approach is likely to be more effective at those small scales. I'm
Mhm.
not saying we would ever want to use this at large scales. As Ileana over here knows, we wouldn't want to use this at large scales. I'm not saying we can replace current technology at large scales. We're aimed specifically at small scales where that technology just isn't working.
Mhm. And what are edge flames?
Okay, well, getting back to the theme of turbulent combustion, if I start to stir, you know, a mixture, fuel or mixture too intensely and try to propagate a flame through it, before I even get to the point where the flame extinguishes completely, that I will start to open up holes
Mhm.
within that flame. And the question, once I get a hole, a region of very intense turbulence will tend to rip the flame apart. And once I get this hole, what will happen to that hole? Will the hole eventually heal itself up, or will it act like a zipper effect and cause the whole flame to extinguish? So
Mhm.
the edge flame is basically just the region, the interface between a burning region and a non-burning region. And so I want to see whether the flame will advance into the burning region or retreat, into the already burnt region and then cause the whole flame to extinguish. And so we've done a number of experiments, both for pre-mixtures of fuel and air, as well as non-premixed flames. Let's say you have fuel coming from the top, air or some other oxidizer coming from the bottom. You can form a sheet of flame between those. And we're looking at both the pre-mixed and we call their type non-premixed. And we've looked at both propagating and retreating flames and different types of fuels with different chemistries, different characteristic diffusivities, which it turns out affects their behavior a lot. So we've tried to map out the whole space of what can happen in edge flames.
Mhm. And what are Haley-Shaw cells?
Rayleigh-Shaw cells, sure.
Yeah.
So one of the things we're interested in is what happens to flames in confined spaces. Most people do experiments on flames, do it in some sort of an open geometry, either a Bunsen type flame or a counterflow of two jets impinging on each other, or in a big chamber where you ignite the flame mixture in the middle and watch a quasi-spherical flame expand outward. Those are sort of unconfined geometries that we use in the laboratory most of the time. However, most applications are in very confined geometries, either a gas turbine combustor or in the space between the cylinder head and the piston head and internal combustion engine. It's a very confined space. And we found that flames burn very differently in this confinement than in an unconfined flame, where basically it's a lot of it's based on the fact that the gases expand tremendously by about a factor of 7 uh, during the combustion process. And so if you restrict it so that the flames have the burnt gas has nowhere to expand to, the flames behave very differently than if they're in an open flame. And so we want to characterize that because we think that's going to affect then how flames burn. Well, it's known that it affects how flames burn in, for example, piston cylinder engines.
Mhm. And I probably should have asked this earlier, but on to the alternative payload specialist. What was some of the training that you had to go through to be an alternate payload specialist?
Sure. Well, there's really two types of training. There's orbiter related training
Mhm.
that involves, let's say, using the launch and entry suits, the orange suits, living in space, how to eat in space, how to go to the bathroom in space. That's when I give this kind of a talk to kids. That's one of the questions I always get is how do you go to the bathroom in space? And the answer is it's sort of like a porta potty, but with two important differences. One is there's a fan, so everything goes in the right direction. And there's also a seatbelt, so you don't float away at an inappropriate time.
Mhm.
So using all of the orbiter related equipment, camera and Earth observations, using cameras, using you know basically all the facilities, learning how to like wash your hair in space, things like that. They use a waterless shampoo like they use for people in hospitals that are too ill to actually get up and take a shower. And then there's the payload related training. Now, in this case, the payload was the Space Lab module that had a lot of experiments in it. So I spent many, many weeks in Huntsville, Alabama, where that training was done, learning about all the experiments, what the principal investigators, I was one of the principal investigators, but learning about every principal investigators, what were they looking for in their experiments, how to do how to perform their experiments, what to look for, what to do if something broke, go through all the repair procedures. We actually spent a lot of time rewriting the procedures that had been developed because although I'm not saying the procedures were poorly written, they were actually well written, but we realized that it would be much better if they were written in a different way, at least from the user's point of view, so that it would be clearer what to do, and also particularly if things went wrong, what sort of your decision tree as to how to proceed. Or to say, like even one example is there was one procedure where you were supposed to put a ruler in the experiment, and so we'd have a scale. So you put the ruler in, then you take the ruler out, you button up the experiment, put the camera in place, put the ruler in there, take the ruler out, and then you're ready to do the experiment. The problem is there was no point in the procedure which said take a video of the ruler.
Mhm.
So I had to call up the project manager on that and say, hey, we really need another line in the procedure here, to actually take a video of the ruler. So then when you remove it, so you can do the experiment, you'll know what the scale was. So like I say, there was a lot more payload related training overall. We spent many, many weeks there, because that was basically sort of our thing. Because there are many other crews also training. You don't get as much time, say um, at the Cape or at the simulators in Houston, working on the orbiter related training. And then you also do some things like there was water survival training. There was, they spin you up through the centrifuge, so you feel the same sort of profile that you would feel during launch.
Mhm.
My reaction to that was, really, this is all it takes to get into space? Because actually on the space shuttle, it was only 3 Gs. 3 Gs is just not that much.
Mhm.
Especially, you're strapped in and the G vector is pointing right into your chest. So it's really not that difficult to manage. I mean, it's unlike the Mercury days. I think on Mercury, the maximum Gs was something on the order of 7.
Mhm. So, what is a big milestone that you're looking forward to in your research?
Well, what I'd really like to do, one of the things I'd like to do is, and the way I start this conversation is I typically am in an audience with a number of foreign students. And so I ask them, well, how many of you are foreign students? A bunch of people raise their hand and say, well, how did you get here? How did you get to wherever we are? And let's say, well, took an airplane. And I said, well, what was the energy storage medium, for the airplane? They say, well, jet fuel. I say, okay, why jet fuel? Why not a battery? And they think about it for a second. They say, well, because batteries are too heavy, or more specifically, the energy per kilogram of batteries is far less than that of jet fuel. And then so I say, well, do you have a cell phone? Of course, everybody has a cell phone. And so is there jet fuel inside this cell phone? And I say, well, no, there's a battery. And I said, why? Why is that? You just told me that fuel has much more higher energy density than batteries. So why aren't you using fuel in there? And they think, why aren't we? And the answer is We don't know how. The same thing we do everywhere in the world every day at large scales. We turn fuel either into electrical power, shaft power, or propulsive power. We still cannot do effectively at small scale. So one thing that I'd really like to do is to be able to replace the batteries, in phones or this laptop computer I'm sitting in front of, with fuel-driven devices, because I don't have to be as efficient as internal combustion at large scale, because the energy density of batteries is only about 1/50th, 1/50, that of fuels, of hydrocarbon fuels. So even if I'm only 10% efficient, that's still 5 times better than the best battery. I mean, a 10% efficient car, nobody's going to buy a 10% efficient car, but that's all I need to do to be much better than the best battery. So it requires a combination of how do I first make the fuel react with air? Also, then what mechanism do I use to convert that reaction into electricity? Do I use thermoelectric devices, which basically convert heat transfer into electron transfer? Do I use fuel cells that use the electrochemical potential difference between the fuel side and the air side of the fuel cell itself, or some other process to convert the fuel, ultimately start with fuel and convert it into electricity? Then another problem that always comes up is, okay, if I'm going to use fuel, I also need to get air from the ambient environment. But the thing is, the air wants to go in at the air is coming in at 1 atmosphere, but I also got to push it out at 1 atmosphere. So I need to have some sort of a pump or some kind of device to make the stuff go in, because otherwise, if it's 1 atmosphere in, 1 atmosphere out, nothing's going to happen. So we're looking at ways of doing pumping, air pumping, without any moving parts. Again, notice the theme of, I don't want moving parts, because at that scale, they don't work very well. They're very inefficient. They're very unreliable. So we've come up with ways using a process called thermal transpiration to obtain gas flow without any moving parts, and using the fuel itself as the energy feedstock, not using electricity. Because if I have to run a pump or something with electricity, I'm trying to generate electricity. I'm going to use up most of my electricity to drive this pump, and I may not get any net power. So again, we're trying to, you can see the themes here: no moving parts, take advantage of what happens at small scales, as opposed to taking something that works well at large scales and trying to shrink it down to small scales. They're kind of the overlying themes.
And lastly, to high schoolers like me and to younger generations that want to become aerospace engineers and even astronauts, what would be your advice to be successful in this career?
I would say the main thing is do something that you love doing, because specifically talking about the astronaut part, no matter how competent you are, no matter how well you play your politics, no matter how lucky you get, chances are 99.9% that you're not going to get selected. So you better be doing something along the way that you enjoy doing. Otherwise, you're going to be pretty unhappy. And let's put it this way: if you're not happy with your job and now you start to go for an interview for an astronaut position, do you think you're going to interview well? Probably not. So I would say the main thing is do something that you enjoy doing. In terms of sort of specific, if you enjoy these things, I'd say sort of an ideal path is one that some people that I know followed. I can think of one person in particular. His name was Tom Jones. I interviewed, not for the payload specialist, but before that, for the mission specialist program. I got to the finalist stage some years before that. And in my interview group of 20, there were 4 people that in my own mind, I thought were going to get selected. I wasn't one of them. And 3 of them did. And the 4th one got selected 2 years later in the next round of applications. And I'm thinking about one person in particular. I thought, this guy has it all. So his name was Tom Jones. He had gone to the Air Force Academy. Then he flew B-52s. And then when he left the Air Force, he got a PhD in astronomy. And then he had a desk job for the CIA. Not a spy job, but more, I think, of course, he couldn't tell me what he was doing, but I think what he was doing is along the lines of monitoring, spy satellite contracts, things like that. So he kind of had everything. He had the aviation experience, he had the military experience, he had the civil service experience. He kind of had, all the boxes checked. So whether he did that, and he had the academic experience, so he kind of had it all. And um, I don't know if he did it because he thought he really wanted to do all those things, or if he thought, hey, this is going to qualify me for the astronaut program. But um, whatever it was, he was very successful. Another person who was also I picked to get selected and did. His name is Rich Searfoss. He had been he was another Air Force type, gone to the Air Force Academy and was a test pilot. And on the first day of the interviews, or a first day of presentations, he came up to me as we were walking out because we had already introduced ourselves. And he said, "Did you go to Caltech 10 years ago?" I said, "Yeah." They said, "I'm Rich Searfoss," and kind of thought. I kind of vaguely at one point, oh yeah, I remember they were the people that did this experiment. He was, and uh, and he said something that was very telling. He didn't, and I said, "Man, I didn't remember you at all, but now that you reminded me, oh yeah, now I remember who you are." I said, "Man, you're really good with names." And he didn't say, or I said, "Yeah, that's amazing. You could do that." He didn't say, "Oh yeah, I'm good with names." He said, they teach us well in officer training school. You see that he didn't take credit for it himself. He gave credit to other people.
Mhm.
He gave credit to his training. So that's actually, I think, important in this because in the astronaut corps, they're not looking, for people. I realized kind of when I walked out the door, I'm probably not what they're looking for in terms of the mission specialist, because they're looking for team players. No one in my field was chosen or promoted because they were a good team player. They were always chosen because they were thought to be an outstanding individual. And you try to cover that up, but little things come out. Like for example,
Mhm.
I was asked during the interview, I put on my application that I was for our intramural team. I was the captain of our intramural hockey team, and so
Mhm.
they asked, "Well, why do you like hockey?" And I said, "Well, I like the speed and the skill that's required, and the contact and the action, all that." And of course, as soon as I walked out the door, I realized the right answer would have been, "I like the teamwork," but I hadn't. It's one of those things. That was the right answer. And this is a piece of advice to almost anyone in any job other than mine
Mhm.
is even if you're applying for a job as a lighthouse keeper or forest fire lookout, where you're by yourself all the time, when you're asked what's your best qualification for this, you should say I'm a team player, because that's what people want, or at least what they think they want.
Mhm.
So that's another piece of advice in terms of the aerospace, becoming an aerospace engineer in general. Um, I'm a big fan of the saying that, chance favors the prepared mind, or the harder I work, the luckier I get. That was originally a golfer by the name of Gary Player uh, said that. And, you think about it, that makes perfect sense in golf. No one is lucky enough to hit a hole in one every time. But the harder you work, you know, you're not going to get a hole in one every time, but you'll get closer to that hole. So, and so many of the things that happened to me during my whole career were the result of, some lucky event, serendipitously. So, always be prepared for these chance encounters with people, or in the case of research, you know, when you see something odd in your experiments, don't just say, oh no, the experiment went wrong. You think, why did it do that? Because almost every great scientific discovery was the result of an accident. I'll give you just one example: radioactivity. Henry Becquerel, just by accident, found that when he put uranium salts on a photographic plate, they would be exposed even in the dark. It turns out someone had found the same thing 50 years earlier, but that person said, "Oh, geez, look, my plates are ruined. I got to start over. I'm never going to put uranium salts on my plates anymore." But Henry Becquerel said, "Whoa, this is interesting. Why is it doing that?" And so, he then discovered radioactivity from that. I could give you many more examples. In fact, on my website, there's a whole presentation about serendipity and contrarianism, and scientific research.
All right. Well, thank you for joining me, and thank you for letting me interview you. That
Okay, well, all right, thanks. Good luck with your project. You,
Mhm.
you interviewed some very impressive people, and I wish you all the best.
All right. Thank you.